Our universe is a vast and mysterious place. It sparks our curiosity with its countless stars, galaxies, and celestial wonders. For centuries, our understanding of the universe's origins was shrouded in myth and speculation. However, in the 20th century, a revolutionary idea emerged that forever changed our cosmic perspective: the Big Bang Theory. This theory suggests that our universe originated from an extremely hot, dense state and has been expanding and cooling ever since. It's a story of incredible transformations, from the formation of the first atoms to the emergence of life itself. This essay will take you on a journey through the cosmos, exploring the Big Bang and its implications for our understanding of the universe. Imagine a time when our universe, with all its vastness, was compressed into an incredibly tiny, hot, and dense point, smaller than a single atom. This point, known as a singularity, contained all the matter and energy that would eventually become everything we see around us. The Big Bang Theory posits that around 13.8 billion years ago, this singularity began to expand rapidly. It's important to note that the Big Bang wasn't an explosion in the traditional sense, like a bomb detonating in space. Instead, it was the expansion of space itself, stretching outward in all directions at an unimaginable rate. As the universe expanded, it cooled, allowing energy to convert into matter, according to Einstein's famous equation, E equals mc squared. The Big Bang model doesn't attempt to explain what caused this initial expansion, or what, if anything, existed before the singularity. The Big Bang Theory isn't just a compelling story, it's backed by substantial observational evidence. One of the most compelling pieces of evidence came from astronomer Edwin Hubble's groundbreaking observations in the 1920s. Hubble discovered that galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This observation, known as Hubble's law, implies that the universe is expanding, just as the Big Bang Theory predicts. Another crucial piece of evidence is the cosmic microwave background radiation. This faint afterglow of the Big Bang was discovered in 1965 and provides a snapshot of the universe when it was just about 380,000 years old. The CMB's existence and its specific temperature pattern align remarkably well with the predictions of the Big Bang Theory. These two pillars of evidence, Hubble's law and the CMB, provide strong support for the Big Bang Theory. They demonstrate that our universe is indeed expanding and that it originated from a hot, dense state billions of years ago. The early universe, just moments after the Big Bang, was a chaotic and energetic place. As the universe expanded and cooled, this primordial soup of particles began to coalesce into more familiar forms of matter. Around 1 second after the Big Bang, the universe had cooled enough for protons and neutrons, the building blocks of atomic nuclei, to form. Over the next few minutes, a process called Big Bang nucleosynthesis occurred, forming the lightest elements, primarily hydrogen and helium, in a specific ratio that we still observe in the universe today. It took another 380,000 years for the universe to cool enough for electrons to finally combine with atomic nuclei, forming the first neutral atoms. This event, known as recombination, marked a crucial transition in the universe's history. With the formation of neutral atoms, the universe became transparent to light, allowing the photons that make up the CMB to travel freely through space. While the Big Bang Theory successfully explains a wide range of observations, it also faces some significant challenges. Two of the most prominent puzzles are the horizon problem and the flatness problem. The horizon problem arises from the remarkable uniformity of the cosmic microwave background, or CMB. Observations show that the CMB has almost the same temperature in all directions, even in regions of the sky that are so far apart that they couldn't have been in contact with each other since the Big Bang. This uniformity is puzzling because, according to the standard Big Bang model, different regions of the early universe wouldn't have had enough time to exchange heat and reach a uniform temperature. The flatness problem concerns the geometry of the universe. Observations suggest that our universe is remarkably flat, meaning that parallel lines will remain parallel forever. However, The standard Big Bang model predicts that even tiny deviations from perfect flatness in the early universe would have been amplified over time. These two problems suggest that something might be missing from the standard Big Bang model. To address the horizon and flatness problems, physicists introduced the concept of cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid, exponential expansion. Imagine a tiny balloon suddenly inflating to the size of a football field in a fraction of a second. During this brief but dramatic period, the universe expanded by a factor of at least 10 to the power of 26, stretching out any initial curvature or temperature variations. Think of a wrinkled tablecloth. If you quickly pull the tablecloth taut, the wrinkles will smooth out. Similarly, cosmic inflation stretched the fabric of space-time so rapidly that any initial inhomogeneities were smoothed out. The idea of cosmic inflation might seem radical, but it elegantly solves several problems with the standard Big Bang model. It provides a mechanism for the universe to become incredibly uniform and flat, even if it started from a more chaotic and heterogeneous state. To understand how cosmic inflation solves the horizon and flatness problems, let's visualize the universe as a balloon again. Imagine that before inflation, the balloon was tiny, and its surface was covered in wrinkles and bumps, representing temperature and density variations. During inflation, the balloon expanded incredibly rapidly, stretching its surface so much that the wrinkles and bumps became practically invisible. This smoothing effect explains why the CMB appears so uniform, even though different regions of the early universe were initially causally disconnected. Inflation also addresses the flatness problem. Imagine drawing a triangle on the surface of the balloon before inflation. As the balloon inflates, the triangle's angles will become closer and closer to 180 degrees, approaching the geometry of a flat surface. Similarly, cosmic inflation stretched the fabric of space-time so much that any initial curvature was flattened out. In essence, cosmic inflation acted as a cosmic iron, smoothing out the wrinkles and bumps of the early universe. Cosmic inflation isn't just a theoretical curiosity. It makes specific predictions about the patterns we should observe in the cosmic microwave background, or CMB. These patterns, known as primordial fluctuations, are like tiny temperature variations in the CMB, representing the seeds of structure formation in the early universe. Inflation predicts that these primordial fluctuations should have a specific statistical distribution, known as a Gaussian distribution, and that they should be nearly scale invariant. These predictions arise from the quantum fluctuations in the early universe that were stretched to cosmological scales during inflation. Remarkably, observations of the CMB by missions like WMAP and Planck have confirmed these predictions with astonishing precision. These observations are like finding the fingerprints of inflation imprinted on the CMB, confirming its role in shaping the early universe. Cosmic inflation has profound implications for our understanding of the universe and its origins. One of the most intriguing implications is the possibility of a multiverse, a vast ensemble of universes, each with its own set of physical laws and constants. According to some inflationary models, our universe is just one bubble in a much larger multiverse, like a bubble in a pot of boiling water. In this scenario, inflation never completely ends, and new universes are constantly being born from the quantum foam, each with its own set of properties. The multiverse concept is highly speculative and currently beyond the reach of direct observational testing. However, it offers a tantalizing glimpse into the vastness and strangeness of the cosmos, suggesting that our universe might be just one of many. The Big Bang Theory, augmented by cosmic inflation, has revolutionized our understanding of the universe's origins and evolution. It has provided a compelling framework for explaining a wide range of observations, from the expansion of the universe to the patterns in the cosmic microwave background. However, our journey of cosmic discovery is far from over. Many mysteries remain, such as the nature of dark matter and dark energy, the physics of the singularity, and the ultimate fate of the universe. These unanswered questions continue to drive scientific inquiry, pushing the boundaries of our knowledge and imagination. Ongoing and future research promises to shed new light on these cosmic enigmas. The quest to unravel the mysteries of the cosmos is a testament to humanity's insatiable curiosity and our drive to explore the unknown.